This is the story of a big and unusual construction job. The building of the Perkins Theological Quadrangle at Southern Methodist University. It is big because it is comprised of 7 buildings complete with library, chapel, classrooms, offices, and residence halls. It is unusual because it is a college within a university, a college which was all built at one time. Completed in 1951, these buildings were the culmination of the dreams and deeds of persons who saw the necessity of a plant of this size as a home for the School of Theology. But a little more than 2 years before, the site was but a barren field, and the buildings were only blueprints, lines on an architect's drawing. The first step in the beginning of this project is the architect's plans, the creation of a proper design. The architect, Mr. Mark Lemon, presents preliminary plans to Dr. Humphrey Lee, president of the university, and Dr. Eugene B. Hawk, dean of the School of Theology. The design of the plant must necessarily incorporate into the style and beauty of the buildings the practical requirements of their everyday use. Then the architect makes comprehensive and detailed blueprints from which the contractor will translate these plans into bricks, stone, steel, and mortar. This, then, is the origin of the physical plant. Lines, figures, specifications, plans on paper. Transforming these plans into finished buildings is a tremendous task. The next step in this undertaking is the selection of a contractor, the persons responsible for carrying out the architect's plans accurately, economically, and with appropriate speed. The contractor selected for this work was the Henger Construction Company of Dallas. Before work can begin, a contract with the university, setting forth the responsibilities of each party, must be signed by both parties. Dr. Lee signs the contract on behalf of the university. And Mr. W.C. Henger of the Henger Construction Company signs for his firm with Dean Hawk acting as witness. The first task at the building site is to construct a tunnel which will lace all the buildings together underground and connect with the central power plant of the university. This tunnel will carry chilled water for air conditioning, high pressure and return steam for heating, and all utilities. A dragline with a 3/4-yard dragline bucket scoops out the dirt in huge bites. 19,000 cubic yards of dirt were removed from this excavation, which will total 2,000 feet in length at a depth of 10 feet. All the earth removed is stockpiled and used in landscaping sites around the Quadrangle and other areas of the university. After the excavation is complete and the foundation for the tunnel is prepared, forms are then built, and the tunnel formed with concrete. Its interior dimensions are 4 feet wide by 6 feet deep. Ready mixed concrete is used for this job to effect savings in the cost of placing the concrete. At the same time, the excavation is made for the first building to be started. For the dormitories, a pan system is used in forming the ground floor, which will be constructed 3 feet above the excavation floor to provide access to the utility piping underneath the building. The removable pans are set with space around them for the reinforcing steel bars, and the reinforcing steel mesh is held slightly above the pans, allowing the concrete to completely surround it. Metal sleeves to provide the proper holes for pipes and conduits that are to go through the floor are placed accurately in position. On the day of pouring concrete, a big machine called a mixer-mobile mixes the concrete to proper proportions right on the job site. The concrete, which is mixed to the architect's specifications to withstand 2,500 pounds per square inch of pressure when set, is fed into buggies through large hoppers. It is a short journey from the machine to the job. Movable wood runway boards are placed across the forms to handle the buggies from the mixer to the pouring area. These are moved as the pouring progresses. Every mechanical device possible is utilized. When it is time to pour concrete on any large surface, it means lots of activity, for all the concrete must be spread at one time so that it will set at one time. This means coming to work early and staying late. In order to prevent honeycombing in the concrete and to force it into small areas, vibrating machines are used. These machines vibrate at 12,000 revolutions per minute and are powered by both electric and gasoline motors. When the concrete is in place, the conduits and sleeves are in their proper position in the floor. Sometimes Texas afternoons can get pretty hot, and even the best of workmen may slow down late in the afternoon. Watch out, men. Here comes the boss. Another thing the contractor has to think about, the weather, especially during the early construction stages, when snow or heavy rains can ruin materials and cause work to be redone. Consequently, a constant check with the Weather Bureau is kept in order to anticipate unfavorable weather. With the first floor complete, second floor forms are next prepared, with the supporting columns being poured first. Column clamps hold the forms for the columns in place and resist the pressure of the concrete. The floor forms and pans are then constructed on these supporting columns. Carpenters expertly build the wooden forms by hand, for they must be extremely accurate. When the concrete is set, the wood forms are removed, leaving the concrete structures in place. Third floor forms go up as soon as the second floor shell is complete. Concrete for these upper floors is carried up on a hoisting tower. In pouring the supporting piers for the library building, special slides are built to handle the concrete. The concrete is dumped onto the slide by a scoop mobile, which has received its load from a nearby mixer mobile. The mixer mobile, which will handle 40 to 45 cubic yards of concrete per hour, is used in most operations because of its mobility and large capacity. The dry mix or aggregate, properly proportioned by weight, is brought to the mixer mobile by truck and is fed into the skip in proper amounts to give a 3 cubic yard yield. The skip is hauled up to the mixer and its contents emptied into the rotating drum, where the proper amount of water is added. The initial lifting of the concrete by the mixer mobile is the only lifting operation performed, as gravity is used from there on in transferring the concrete to other equipment. Automatically, the giant machine performs all the necessary operations, filling, mixing, lifting, and dumping it through hoppers to the waiting scoop mobile, which will carry it off to the prepared forms. After the supporting piers have been completed, the forms are prepared for the ground floor of the library. Steel mesh reinforcement again is used for the concrete slab, and the 2x4s running horizontally across the forms are screeds and indicate the top level of the concrete floor. Slides are also built for placing concrete from the ground above. As before, a mixer mobile feeding concrete buggies is used in the pouring operation. But in addition, slides are used to carry concrete from a second mixer mobile. Concrete is dumped from the second mixer-mobile directly into a waiting bathtub truck. The truck then drives directly to the slides, where the concrete is poured down the slide and into its place in the forms. The use of two mixer-mobiles increases the speed of pouring, and the slides more easily reach some of the pouring area. The concrete is leveled by hand in line with the screeds, previously placed to determine the right height. Structural steel is used in the library because of the heavy loading and the long spans of open space required. With steel, the need for a large number of inside supporting columns is eliminated, allowing these large open spaces within the building. All the steel was fabricated locally, cut and punched to fit, and delivered to the job site ready to be erected. The steel beams are fastened together with 3/4-inch rivets. It takes a crew of 4 men to do this job. The forgeman heats the rivets and tosses them one at a time to the catcher. A man called the bucker-up stands behind the rivet, bracing it with a tool called an air jam, so that the riveter can drive the rivet firmly into place. A total of 347 tons of structural steel went into the library building. Another time and cost-saving operation is the use of a ditching machine to open ditches for sewer and water lines. The gasoline-powered machine, taking the place of about 25 men doing hand labor, scoops the earth up in buckets and dumps it on an endless fabric belt, which deposits the dirt alongside the trench. On this job, the contractor opens only about 300 to 400 feet of ditch per day. The machine can do much more, but he opens just enough for one day to guard against having the job ruined by rain. A hard rain into a freshly opened ditch could mean the job must be redone. Pouring the steps on the chapel presented a problem of placing concrete in the staggered sloping forms. Since the area is inaccessible to buggies or trucks, the concrete is dumped at this site by a 3/4-yard hopper, fed by a truck and lifted by a crawler-type crane. The hopper is filled from a bathtub truck, which is fed from a nearby mixer-mobile. Here again is an example of how the contractor must use his ingenuity in executing the work in the most efficient and economical manner. Staggered construction of the whole project was planned so that equipment could be shifted from one building to another for maximum efficiency and economy. A foundation for one building goes in as another building nears completion. Proper machinery makes excavation a relatively fast job. One machine picks up where another leaves off. After a drag line has made the rough preliminary excavation, these two, the bulldozer and the scoop mobile, work in conjunction with each other to make a cleanly finished job. The bulldozer loosens and scrapes the earth to a uniform level, piling the dirt where it can be removed by the scoop mobile. The scoopmobile then follows the bulldozer, picking up the loads and carrying them to trucks for removal. Some jobs, like this pier hole, must be done by hand. However, a mechanical air spade helps out. Of course, in small areas, finishing touches are done by manual labor. And that Texas sun can certainly produce a suntan. On the chapel, again structural steel is used because of the large open space required within. With the framework complete, preparations are made for hoisting the spire into position. The spire, although approximately 50 feet long, is relatively light, weighing only 3 tons. It is made of prefabricated steel and reaches the job site in 2 separate parts, which are put together on the ground before it is ready to lift into place. A special crane with a 60-foot boom and 15-foot jib will lift the spire to its final position on the chapel frame. The move covers a vertical distance of about 60 feet from the ground to the base of the spire. First, the men who will fasten the spire in position ride the big crane to their high perch. They will fasten the spire with erection bolts, which are later replaced by permanent rivets. After the men are in place, the crane with its giant boom begins to lift the spire carefully toward the base. The crane operator must know his job, have perfect timing, and his equipment must be in top shape for a job like this. One mistake could break the rather delicate spire or send those men hurtling to the ground. On the complete quadrangle job, all 7 buildings and more than 2 years' work, there was not one major accident. Although the spire itself was built away from the job site, when it was finally hoisted into place, it fit well within the allowed tolerance of 1/32 of an inch. As soon as the structural work of each building is complete, work begins on the inside. Plumbing pipes, conduits, and ductwork, the arteries which supply the utilities to the building, are installed and connected. Some of the metal parts for this interior work are fabricated in the nearby welding shed by arc welders. Pipes and ducts are fitted in the holes left in the concrete for this purpose. Since the chapel, library, and classrooms are air-conditioned, ducts for that purpose are installed at this stage. At the same time, on another building, the brickwork is going on. Bricks and mortar are hoisted to the working levels by means of a hoisting tower. These towers, operated by gasoline engines, are necessary in handling the many tons of material used in the construction work. The bricklayers are furnished a constant supply of bricks and mortar so that no time is lost due to lack of materials at the working area. Ready mix mortar, to which cement, waterproofing, and add mix have been added, is used. In the hands of skilled experts, bricklaying becomes a simple, fast job. Incidentally, the movement of the scaffolding causes the apparent swaying of the walls. Strings are stretched across the face of the brick to give a plumb line. The face brick was manufactured in Arkansas, where the clays to bring about the required color are found. It is called Fort Smith velour texture mingle shade face brick, and over 500,000 were used in all. All outside walls are 13 inches thick, 4 inches of brick laid against an 8-inch tile base with an inch of mortar between. Tubular steel scaffolding is used throughout this job because it can be raised and lowered and moved from one site to another quickly and can be set up by common labor. This eliminated the need for constructing wooden scaffolds and tearing them down after completion with a resultant fire hazard. Architectural and engineering students from many universities in the area are interested visitors as this project progresses. Members of the contractor's staff show them around and explain the details of construction. Thus, they gain first-hand knowledge of practical construction methods. Of particular interest is the oolitic limestone to be used on the buildings. Columns, trim, sills, and cornice are formed of this white cut stone. The number on each stone corresponds exactly with one on the blueprints denoting its proper position. Stones for the cornice, weighing about 800 pounds, are hoisted into place by a crane. These stones were brought in by truck from Russellville, Alabama, where they had been intricately cut to exacting specifications. Although they were cut 1,000 miles away, when set, all fit perfectly. Masons carefully prepare the mortar base for the stones so that they fit precision-like into their designated positions. The clearance between stones is only 1/4 of an inch. Close cooperation between the setting crew and the crane operator is required in handling these huge stones, for one slip could cause the loss of a hand or arm, or even more serious injury. Each stone is carefully fitted into its exactly designated location. Holes previously cut in the stones provide a place for the attachment of this steel hoisting apparatus called pin Lewises. As each stone is set, the pin Lewises are removed for hoisting the next stone. Final setting into place is done with a rubber mallet. One by one, the heavy stones are hoisted to the cornice for careful setting, each time checking to be sure the number on the stone corresponds with the proper number and position on the blueprint. Overhanging stones on the cornice are anchored with bolts as well as mortar, giving them an extra strength in their position, high above the ground. These anchor bolts are previously set into the base on which the stone rests and are securely tightened with wrenches. When each stone is accurately set, mortar is poured around the edges to give a smooth, secure joint. Two of the buildings, the library and administration buildings, are topped by gold cupolas. Although the buildings are in different stages of construction, the cupolas are put up at the same time for efficiency and economy. Completely prefabricated, The cupola is raised to position by a crane and gently set into its prepared base. Flatbed trucks carry the cupolas to the building site where the crane is attached to an eye in the top of the cupola for hoisting. Each cupola has a steel frame with a copper exterior, and each is 12 feet square at the base. After they are in place, they will receive a coat of gold leaf paint. Although this paint actually does contain gold, its cost is not much more than ordinary paint. The workman riding the cupola is not there just for the fun of it. Actually, his job is to remove the hook from the eye when the cupola is finally set in place. And how does he get down? He simply climbs aboard the headache ball and rides back to the ground. The different stages of construction made it necessary for him to ride up in one case and not in the other. Just as in the case of the chapel spire, the cupolas were constructed away from the building site, but when placed, they fit perfectly. Inside, metal door frames are set up in advance of interior walls. Metal frames provide longer life than wood frames, and consequently they are used for permanence. The base of the frame is fastened to expansion bolts set in the concrete floor. Great care is taken that all doors are plumb. A spirit level ensures correct vertical positioning, and wood braces hold the frame in place until the complete wall is set. Metal lath, set up as a base for the wall, is wired to channel steel, which has been set along the line of the wall from the floor to the ceiling, as well as across the ceiling itself. This wire lath will serve as a reinforcing base for the plaster. Skilled workmen called lathers expertly wire the lath in place, inserting the wire, twisting it, and biting it off, all in one operation. For electrical outlets which will project through the wall or ceiling, the lath is placed over it and then carefully trimmed around the fixture. Even with heavy cutters, the workman is accurate and fast. When the lath is set, the plasterers begin. Instead of the customary gypsum plaster and sand, the contractor for this job used a mixture of gypsum plaster and a volcanic material called perlite. This mixture is lighter in weight, and although it costs more as a material, it costs less on the wall. Because of its lightness, men can put it on more rapidly than ordinary plaster. Notice the swift, sure strokes of the workman in placing the plaster on the wall. It stays on the wall, too, not ending up on the floor. A trowel is used for placing the plaster, and the board carried in the other hand is known as a hawk. This first application, the scratch coat, is the rough plaster, and is covered with a second course known as a brown coat, and then a third course, which is given an even finish as the interior wall face. As the interior finishes are applied, final touches are added to the exterior, including the trim painting. In the hands of experts, the paint goes on the woodwork and not on the glass. walks are used throughout the grounds to fit in with the Georgian architecture. These are laid on a concrete sub-base for greater durability. Extreme care is taken to ensure that the bricks will form a uniformly even surface, for any irregularity would be readily noticeable. The spire receives its finish of lead-coated copper as the exterior of the chapel is completed. Thus, in just over 2 years, a bare field has been transformed into the home for a school of theology. These 7 buildings, the Bridwell Library, Kirby Hall, A. Frank Smith Hall, S.B. Perkins Hall, Paul E. Martin Hall, Eugene B. Hawk Hall, and Perkins Chapel, were made possible by the efforts of many individuals, by the vision of educators who built a need for such a school, by gifts of Mr. J.S. Bridwell and his daughter, Mrs. Margaret Bowdle, and Mr. and Mrs. Joe J. Perkins, gifts which provided the necessary funds for such a project, and by the efforts of the Henger Construction Company, whose vast experience, technical knowledge, and engineering ability made possible the completion of this quadrangle within the allotted time and with every specification carried out to the most minute detail. 9,000 yards of concrete, 2,000 tons of steel, 36,000 cubic feet of stone, and over 500,000 bricks have been molded into these beautiful buildings by the diligent and expert performance of a most capable and reliable construction firm, the Henger Construction Company. This, then, is the case history of the Perkins Theological Quadrangle.